All right. Good morning, everybody. Let me just help this person out here. There we go. All right. Nope. Wrong chat room. We want to be in the main classroom chat. Okay. As always, before we begin, I would just like to get confirmation in the chat or in voice that you can both see and hear me, just so everything is good to go. Perfect. If at any stage you think you should be hearing something or seeing something and something goes wrong, just let me know. If for nothing else, I have to just repeat myself. Sometimes these things happen and I don't know they happen, so I'm always a little paranoid about that. So yesterday we started our discussion with an introduction, and the introduction was on inductive reasoning. Inductive reasoning, if you remember, is where we use or collect some evidence, make some examples, not everything that's possible, and use that possibly limited collection to make a general statement about the situation. And with that comes pros and cons. Pro is that it's easy to do. Usually making an example is fairly easy. But the con is that I'm at the mercy of those examples. And if I don't have enough or enough variety to really represent what could happen, they could lead me to an incorrect conclusion. And I'm never going to be 100% certain in my conclusion because there will always be examples that I don't consider directly. So, how do we get around that with an alternative to inductive reasoning? That is where deductive reasoning comes in. So, deductive reasoning now has the goal to present an argument where at the end I am 100% certain of my conclusion, and there's no doubt. And as such, I can't rely on specific examples. But let's cross over from inductive reasoning to deductive reasoning by looking at our first example, and they're called exercises in the book. So we just have a little game to illustrate the concepts. We have a small little 4x4 checkerboard. I'm not going to read all this. You can if you want to, also after the fact. So we have two player A and B. The first player, player A, has the task of putting 2 pennies somewhere on this board. Then player B's turn comes up and they have to place paper clips on the board, each paper clip covering 2 squares. So here you can see some examples. In the first game, let's see if I can zoom in a lot here. First game here, player A put their pennies on these 2 squares. Now player B has the task of placing paper clips, not overlapping. Each paper clip covers 2 squares, and player B's goal is to cover the whole rest of the board. If they're able to do that, then they win. So in this first example, they were able to do that, and B wins. Next example, player A chooses 2 different squares for their pennies. B was able to still cover the board with their paper clips. B wins. In this third one, player A places the pennies over here and tries, can't place paper clips in such a way that it covers the whole board. So B loses and therefore A wins. And so on and so on. I can make more and more examples. Of course, there will be many, many different examples of games one can make. Sometimes B wins, sometimes A wins, and so on. And again, just as I'm thinking of it, don't ever wait for me to ask, are there any questions, or how do you feel about this, or anything like that. Just if there's any uncertainty about anything, then just say right away, interrupt me, all those things. Okay, so here's our game. Now we have some questions, just getting us thinking in the right direction. And then we will streamline the idea of deductive reasoning afterwards. Let's look at the squares on which pennies were placed. That's what happens first. Could somehow their colors be related to who wins? You know, the more examples I do, it's not a big board, it's not a complicated game. I can start to think, well, the same thing happens when pennies are placed in a certain way. So let's explore that further, because that now suggests a general conclusion. If you conclude, number 2, from these 8 examples that your answer to the first question, whether it's yes or no, or I don't know, I notice a pattern, maybe. If I conclude from these 8 examples that the pattern that I think is there is correct for every possible game, what kind of reasoning am I using? See, it's a question mark. So this is a question to you. What kind of reasoning would I be using if I make any sort of conclusion from the above 8 examples?
Inductive?
That would be inductive reasoning, because I am just using a limited set of examples, whatever they are. They're not all possible games. Do the 8 examples prove anything? Proving means 100% certain in my conclusion. No, that's the downside of inductive reasoning, that it doesn't prove anything with 100% certainty. Sure, if I have millions and millions of examples, then I'm so close to 100%, we sort of feel that it is the same, but it's never truly the same. And 8 examples might not even be close to enough to give me any sort of confidence. So inductive reasoning, no, it does not prove it. So I'm not going to write these down because it's just still an introduction example. I'm never going to put something like this in a test. It's just getting us thinking in the right way. Number 4, according to the rules of the game, each paperclip has to be placed on 2 squares that share a common side. Yes. What can be concluded about the colors of any 2 such squares? Well, if I look at my examples, and of course I'm still limited to that, but it helps me understand the rules of the game, that regardless of where a paperclip is placed, it's always going to be on 2 squares of different color, a black and a white square. Always. That's just how paperclips can be placed, not diagonally. That's how the game works. Number 5, if player B is able to place the 7 paperclips so that they cover all the 14 squares that are left, what must be true about the colors of these 14 squares? Well, if each paperclip individually covers 1 black, 1 white, 2 paperclips will cover the same number, 2 black, 2 white. 3 paperclips, still the same total number of black and white squares. So if all the paperclips are placed, then the squares that they cover have to be the same number of black and white squares. Of the remaining squares, how many squares are there of each color if player A begins by placing the pennies on 2 white squares? What about 2 black squares? What about a white and a black square? So depending on where A, who starts, places their pennies, the number of black and white squares could differ. for player B to place paperclips on. If player A places 2 pennies on 2 black squares, now the number of black and white squares are not the same. But if paperclips are possibly placed, the number of black and white squares will always have to be the same. So that gets us thinking, oh, it seems like if pennies are placed on 2 squares of the same color, then the remaining squares don't have the same number of black and white squares, and how could paperclips then possibly be placed on all of them? So now I'm sort of forming an argument that is essentially deductive reasoning. 7. What kind of reasoning are you using when you conclude from your answers to questions 4 6 that your rule proposed in 1 is correct for every possible game? So now I'm looking at examples, sure, to just better understand the rules of the game, but I'm not limiting myself to any specific example. I'm just looking at them to remind myself how the game works and visualize it. My argument in number 4 to 6 about how the number of black and white squares relate to each other are independent of a specific example game. And I'm now crossing over to deductive reasoning. There are pros and cons to this as well. The pro of deductive reasoning is that if it works, or not if, when it works, if I'm able to make the argument complete and make sense, it's 100% certain that my conclusion is correct. The downside, unfortunately, is it's not even remotely as easy as inductive reasoning. That coming up with this argument can be confusing, and there might be some of you right now that are a little bit confused, like, where is the argument here? I sort of understand, but I don't see it. So for that reason, we have to streamline this and just look at the very basic structure of deductive reasoning to just try and get a handle on it. Because even that checkerboard game and all the words might be a little bit too much for me for my first introduction. Okay, so we want to look at the basic idea of deductive reasoning, but for that I just want to let me just see if I need the issue of a statement right now. I think I'm gonna leave it for now. I'm just gonna focus on the structure of, I have the heading here. I'm gonna write it again. Just indecisive. Deductive. Why is that capitalized? That's not fair. Small r for you, reasoning. Okay. The basic structure. So here is my example that I like to think about, but of course you can put many spins on this. It comes in 3 main parts. The first part is called the premise, and that is something that no one disputes. Everyone accepts as true. It's sort of the heart of this. I have to have something at the core. For example, in the most simplest case, we can say that I have an open field of grass, and I can say that if it rains, then the grass is wet. Now, I don't care about tenses or anything here. If it rains, it results in wet grass. Okay? I'm not looking for technicalities of covering the grass or anything like that. Open field, I'm looking at grass outside my window. If it rains, the grass is going to get wet. No one doubts the truth of that statement. We'll refer to exactly what a statement means later. I don't need it right now. We'll need it tomorrow. It's fine. Now, I'm going to actually look outside and make an observation. And my observation could be right now or today or whatever. It is raining. Again, I don't care about the tenses at all. It's raining, it rains. There's rain. I see rain. I can then conclude with 100% certainty that therefore the grass is wet. So I do this without going outside and touching the grass. That would be like making an example, collecting evidence. I'm doing this without that action. So I'm imagining myself, okay, premise is conceptual. I don't do anything, but everyone agrees that if it rains, the grass is going to get wet. Now I look out the window and I see rain. Without going to touch the grass, I know with 100% certainty the grass is wet. So see, it's not the same as collecting evidence and noticing patterns and making conclusions from that evidence. It is a more, I don't want to say higher level, but it's a different kind of argument, independent of the of actually going to touch the grass. And I have 100% certainty because there is 100% certainty in my premise. It's been very quiet, and I feel like I'm talking to myself. So I'll pause here to double check if there are any thoughts about this premise, observation, conclusion structure that I have on the screen. Remember, you get the most out of this if it's a discussion. It's a back and forth. Otherwise, I'm totally guessing how you feel about it. Good. Anyone else? Questions are good. Remember, you're safe behind your screen.
That makes sense.
No one knows who you are, technically. So you can ask anything you want. Perfectly safe. It's actually easier than in a in-person class. No one can even see who's speaking. It's perfect. All right.
I just had a question.
Yes.
So if with the checkerboards, right, it's not deductive reasoning until you've proven that it's a fact, or is something like that just not possible to prove? Like, or is it just too much effort?
We're going to come back. It's how I approach it. If I base my conclusions on the actual examples that I have, those 8 games, then it's inductive reasoning. And I don't know for sure that there might be a game, a board layout that doesn't fit what I think. Just because my 8 examples suggest something doesn't mean it's 100% true in general. But when I have an argument, regardless of any specific example, that argument has the potential of being 100% correct, and then I'm crossing over to deductive reasoning. So it's all a matter of how I'm using my examples. If I'm at the mercy of my examples and I look at the pattern that I observe and say, oh, that happens every time, that happens in general, that's inductive reasoning, and I'm not 100% sure that's true. Deductive reasoning has the aim of trying to be independent of any specific examples and just having a general argument from the start. Like, I don't actually go and touch the grass to conclude with certainty that it's wet. See, there's a difference. I'm not relying on my collecting of evidence, yet I can be 100% certain in my conclusion. That's the distinction between inductive and deductive reasoning. Now, they both have their place in science in general, because if I think about physics or chemistry or things like that, there are times when experimentation and collecting evidence is all I have. But unless I have an overwhelming amount of evidence suggesting the same thing, I can't assume 100% certainty in my conclusions. So what would it look like if I have an argument outside of actual examples, actual evidence? That is deductive reasoning. Now, in the attempt to make it as simple as possible, I feel still a little bit confused about the wordiness of exercise, what was this number? 1.3, about the checkerboards. It's a lot of words. I'm getting confused. So can I simplify it and make it as bare bones as possible? Premise, observation, conclusion is my way of doing that. Maybe let's write conclusion here. Conclusion. Get out of eraser mode. Conclusion. So I want to make it as simple as possible to understand how does deductive reasoning work in essence. And we'll come back to the checkerboard and see, okay, well, how do I now use this three-part structure to make it look a little bit more clear. But for now, let's just have something as simple as I can possibly make it. The rain and the grass is what works for me. Okay. And of course, this is all in the book. I'm just not copying the book word for word here. But it is all there if you want to look and read it in slightly different words. It's all the same. Okay. So this is perfectly fine. There's also an alternative version. Same 3 parts: premise, observation, conclusion. Same premise. It's the same situation. Let's pick the rain and the grass situation again. So if it rains, then the grass is wet. Now I will say in the, deductive reasoning and inductive reasoning, we do use these things without necessarily realizing it. And when it comes to teaching, whether directly or indirectly, I have the task of really having to be much more aware of how these things work so that I can make adjustments and say things in a very specific way based on the needs of the student. So our goal here is to just be very aware of how we think, how we reason, when it's correct, when it's not correct, when it's 100% correct, when it's a little less. So that's our goal here, to just build that awareness of how we reason. So now I have the same premise. If it rains, then the grass is wet. Now my observation is, I go look at the grass. The grass is not wet. Can I make a 100% confident conclusion? Yes, I can. I can say, well, therefore, I don't just pick tenses to make it easy. It didn't rain, or it's not raining, or whatever version you want. That's still a 100% correct conclusion, because the premise is indisputable. It's always true. I have to have that at the core to start the argument. If it rains, then wet grass is a certainty. Now I look, but the grass isn't wet. It's the opposite. Therefore, there is no way that it could have rained, because rain would result in wet grass. So if I see the opposite of wet grass, then the opposite of this raining part must have happened with certainty. So on the surface, they don't look the same, but they are exactly the same argument. And sometimes one is a little bit more convenient than the other. Very often the alternative version is a little bit easier. You'll see once we get to the puzzles, it's a little bit easier to get to that. I sort of get to contradiction. I could say, okay, well, if it rains, grass is wet, sure. Now, I could assume rain, but when I go outside and see dry grass, then that assumption is not correct, and I have to conclude that it didn't rain. It's the exact same argument, deductive reasoning. Any questions on this alternate version of the same thing? So quiet.
Sounds good.
It's good. Yeah.
Okay, good. Okay. Let's see if I have space on my page still. Ooh, I do. Very nice. I have lots of space. Wow. Okay. So now, what about the following? Let's take the premise, be consistent, keep it the same. There's no need to mix it up. If, where's my if? If it rains, then the grass is wet. Same premise. Nothing has changed. Now I observe, let's say I observe wet grass. The grass is wet. If I then conclude, saying therefore it's raining, is that conclusion 100% certain?
No.
Why not? I wrote it down and everything.
It could have just rained.
Well, even simpler than that, someone could have put a sprinkler down or something else could have caused the grass to be wet. So there's an argument that might on the surface feel correct or sound, logically sound argument. But if I observe wet grass, it could be very likely that it was caused by rain, but it's not 100% certain. There is a small chance someone could have just dropped a bucket of water, and then I observed the grass after that. So this form of reasoning is taking the likely explanation as if it was a fact, 100% certain, but it's just likely. So let's say here, this is just likely, not 100% certain. So there's a subtle difference between these two forms of reasoning. I should have made a new page. Now I have to scroll up and down. Oh well. Look at the original version of deductive reasoning. Same premise, so I don't have to worry about that. Here I observe the first part, and that immediately results or leads to the second. In this version, I observe the second part of the premise and assume that it comes from the first, when it doesn't have to. The premise is only one direction. Rain causes wet grass. Wet grass doesn't necessarily come from rain. It's not I'll say a two-directional statement. Don't want to get too fancy with naming these. So this is a form of reasoning. It's just not a logically sound form of reasoning. This is called abductive reasoning. And it's important to be aware of this, because as soon as you really start looking for it, you'll notice that this form of reasoning is what people predominantly use. if you think about the Sherlock Holmes stories, we all think that, oh, he is so logical, he's using deductive reasoning. No, he's not. He's using abductive reasoning. The story continues. He maybe finds a murder weapon or whatever crime occurred, and in the end, he takes the most likely explanation as his conclusion, and it just turns out through the story that it is correct. But he was just eliminating other possibilities until what's left is probably what has happened. It's abductive reasoning. It's not 100% sound, logical reasoning. But in the story, it sounds as if it is. Now, there's nothing wrong with guessing the likely explanation, but I have to be aware that depending on my goal and my needs for this argument, if I need 100% certainty, then I need a form of reasoning that fits that. And guessing the most likely explanation is not sound logical reasoning. And where's my page now? This one. If I look at how students think, I'll put it up here. Hopefully it's not too small. Abductive reasoning happens all the time. Look at this example. A student did a test, and you graded the test. You're the teacher. You give it back. So there's a premise that everyone should agree. So let's just check if we agree that. From the student's point of view, if I answer the question correctly, then I will get the correct final answer. Does everyone agree with that? If I do the question correctly, perfectly, of course I'm going to get the right final answer. Okay, so the premise cannot be disputed in any way. We have to build on that. Now, the student gets their test back. They see, well, I got the correct final answer, but you didn't give me all my marks. Because their conclusion is, if I get the correct final answer, then I must have answered the question correctly. I should get all my marks. And then they are outraged when they don't. It doesn't make any sense to them. Why? Because they're using the likely explanation, answering the question correctly, as 100% certainty. But it doesn't work that way. It's only one direction, the premise. If you answer the question correctly, you'll get the final answer correct. But just because you get the final answer correct doesn't mean you answered the question correctly. Students do, not like little elementary school students, do this all the time. If you think about the following little example, I don't have too many of them, but let's suppose it's you have to simplify a fraction. Let's say 16 over 64. What's that? They're like grade 4, maybe 5. They just cross out the 6's and then get 1 over 4. It's the right answer. It is 1 over 4. But they didn't do it right. That is not how you simplify fractions. You can't just cross out digits as you please. So just because I get the right answer doesn't mean I did the question correctly. In most situations, it is likely that I did the question correctly, but it's not 100% certainty. Yet, if I start to really think about the difference between deductive and abductive reasoning, why one is 100% certain and the other one is not, and notice how people form arguments or conduct arguments, I'll notice that abductive reasoning is the majority of the arguments being conducted. And it's just not, and the downside is there's no problem with going with the likely explanation. The problem is when people assume they're 100% correct. They're absolutely certain in their abductive reasoning. That is the danger. If you admit that it's just likely, well, it's okay. There's nothing wrong with that. But abductive reasoning is not sound logical reasoning. So it's very important to understand the difference between these, and the easiest path I'm going to have is trying to make an example that's as simple as possible. You don't have to use rain and grass. I'm just used to it. You can use other examples, but trying to make this premise, observation, and conclusion as streamlined and simplified as possible to capture the essence of that argument that is trying to happen here. Any questions on the difference, why abductive reasoning is not logically sound? Think about it a little bit and you'll see abductive reasoning is what people do all the time. And there's nothing wrong with that, but they use it and then act as if it's a certainty. And it's not. It's just likely. And there's a big difference between being certain and having a likely explanation. It's not the same thing. All right. It takes time sometimes to think about these things. This first chapter really, on logical reasoning is very much for us to just be extra aware of how we say things, how we think, how we reason, because then we can identify it better in someone else. And maybe you're sitting and you're working with little Timmy one day, grade 4 or 5, and it's important to understand the reasoning that they're using and whether it is sound or not, and how you can adjust it and point out little things and guide them in the right direction. I have to be aware of how I think and how reasoning is done first before I sit in front of a student in real time and have to pick it up and adjust it and say the right thing at the right time. It starts with me first. So we're trying to develop that awareness within ourselves first. And it's things that I might never think about until I take the time to think about it.
I just wanted to ask something real quick.
Yes.
For the first structure of deductive reasoning, if it rains, then the grass is wet. Today it is raining, therefore the grass is wet.
Yes.
Isn't that also just taking the most likely because somebody could have covered the grass, which makes it abductive reasoning?
No, of course I have to, in an attempt to make this look as simple as possible, I have to ignore little technicalities that would complicate this, right? We have to start with the premise and accept that as fact before moving on. And yes, technicalities in reality could happen, but I don't want to complicate things, so we all have to start by agreeing. If it rains, the grass is going to get wet. Assuming open grass, just to keep things simple. It's really just to simplify things as much as possible. Once you start looking at, well, this could happen. Yeah, sure, many technicalities could happen in practice, but it is going to overcomplicate this, and the goal here is to make it as simple as possible. So we have the premise, which is not disputable in any way, and then we'll just build a simple example off of that. These things, the downside of deductive reasoning is that it can get very complicated when you're thinking of all kinds of factors being involved. Our goal here is to just keep it as simple as possible, just strip it down to the bare essentials. How does that look then? But yes, in general, it could be much more complicated. And when we get to our puzzle section, logical puzzles, it will be much more involved to the point where we can't even write all of the argument out. It's too much. But hopefully with this basic sort of template, I can identify the reasoning when we just talk through the puzzles. So yes, we're just trying to keep things as simple as possible. So I'm trying to not think about it too realistically, just open grass, under sky, then the premise is definitely not something that anyone is going to question, I hope. Any other questions? Or a continuation of that question? Or anything at all? As we go, I mean, it's only our second real day, right? As we go, hopefully you'll feel more confident and speak up. If you look at the time, we have 10 minutes left. Those 10 minutes were for the discussion part. And I'm definitely happy that some people have spoken up, but we definitely have time to address any questions you might have. The last thing is I just want to refer back. It's a little hard to see here, but it's going to be simpler if I just read it instead of writing the same words out. Just referring back to the checkerboard problem. How would the most simplest version of the deductive reasoning look for the checkerboard problem? So I have to start with a premise. I have to start with something that is absolutely true, not in question. It could be, if it is possible for player B to cover the board, then the paper clips cover an equal number of black and white squares. Right? The questions sort of led me to that. Well, if B is going to cover the board, there has to be an equal number of black and white squares based on the rules of the game. Not any specific example, that's how the game works. Now I maybe make an observation on a game. One observation could be, player A put coins on 2 squares of the same color. This is just one example. If player A put coins on 2 squares of the same color, then the squares that remain have a different number of black and white squares. Think of the rain and the grass. Premise, if it rains, then the grass is wet. What part do I observe here now? If it's possible for B to cover the board, there has to be an equal number of black and white squares. Now I observe black and white squares that are not equal. So the second part of the premise is not true. The grass is not wet. Therefore, it couldn't have rained. Therefore, it's not possible for player B to cover the board, and player A wins. Just trying to make it as simple as possible. So it might take you some time. Match it with the rain and the grass format and see how this is the alternate version of deductive reasoning. That if it's possible for B to cover the board, there has to be an equal number. I then observe, due to what player A has done, perhaps I observe black and white squares that are not the same number. That is the second part of the premise failing. Therefore, it's impossible for B to cover the board. Do we at least sort of see how this matches the alternate version of the rain grass format? It might take some time. Maybe you have to flip back and forth and look. The raining portion is B covering the board. The grass being wet portion is an equal number of black and white squares. If the second portion fails, then the first portion has to fail based on the premise. So these things take some time, and they certainly get complicated very quickly, which is why we are spending the majority of the time focusing on this simplified, bare bones structure so that I can get a feel for it. If I have to pick out all the premise, observation, conclusion groupings in a larger argument, that is very complicated, especially to do it in real time. To pick up when it's deductive reasoning and when it's abductive reasoning, it can be very complicated. So we are just trying to simplify it to become aware of what works and what doesn't work, and how things are the same and how things are slightly different, and what do I mean by logically sound, 100% certainty, when is it not, just raising awareness and starting to think in the right way. You're welcome to look at problem 1.4, but it's certainly not a test question. It's just something that I have. It's very similar to our checkerboard problem. Look at it, ignore it completely. This is still very much a part of our introduction. And tomorrow we will then continue with chapter 2, which has a little bit more variety when I start looking at puzzles and things like that, where the testable questions will come from. So for now, the only things that you need to know is what are the three main forms of reasoning: inductive, deductive, abductive. Can you give an example of each? And can you state a pro and a con for each? So if you review and you're not sure about how to answer any of that, let me know. But past that, there is nothing to know because it was just an introduction.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.